while, and var.
Sorry, teacher, are you writing?
Oh, yes. So again, it's not working. And the third one is this, while var is different from 0, do something inside. And that's it. We will have just 3 different instructions. And from here, we will see that we can create a lot of all the programs we can imagine. So, well, this is, I think this is surprising because it looks so simple. However, it is not. So, for example, we don't even have instruction for clearing the a variable. By clearing, I mean setting it to 0. So we can define a new program that will be named clear, and it will have as argument a variable. And we can define it by using a colon, just like in Python. Well, of course, you can use a different notation if you want, but we can define this program that will be called clear. And what it will do is, while the name of a variable is different to 0, then just decrement its value. And that's it. So with this simple program, we are using the basic blocks, which in this case are these 3. We are using these basic blocks to create a new program, which will be clear. And as always, you know, this course is always constructing and playing with blocks, just like Legos, or maybe some of you had Tente, I don't think so, or Exin, or I'm going to all. Does any of you have Tente? No. Exin? No. Okay, but you know Lego, right? Okay, so we are building like using Lego blocks construction. So we are doing the same again, but this time these are our basic blocks, our very, very basic blocks. And with this, we create a new tool, and this will be clear. And of course, we need a way of assigning a new the value of a variable to another one. So we will create var uno, var one, sorry. Uno is in Spanish, it's 1. So we want to assign the value of var 2 to var 1, and we will use this notation. So I will skip this triangular braces because now we are speaking about particular variables, but of course we can change them with anything we need. So the program for assigning the value of a variable from one to another will consist first of clearing a new variable, which can be called aux. So this is auxiliary variable. And then we do clear var1, and while var2 is different from 0, then we will increase aux and decrement var2, and that's it. And then we will enter another while cycle when we have aux is different to 0, and then we will rebuild the value of these two variables, var1, and increase var2. And finally, we decrease aux, auxiliary variable, just because we need it to reach 0 and then stop. And that's it. So we have defined 2 different programs here. Our first 2 programs, one is clear, another one is assignment. So this looks a little bit like, well, it's too basic. It should be defined as one of the basic instructions here, but no, not even assignment is a basic instruction of this language. The basic instructions are only these 3. So if you want to see, well, does this really work? Well, let's try it. Let's suppose we want to assign the value var2 equals 3, and let's say var1 equals something else. We don't care, 5. And then we will see how this program works. We have the initial value of var1, var2, and aux. When we start, variable 1 has 5, variable 2 has 3, and aux has something. You can think of anything you want, maybe 8. We don't care. Why we don't care? Because we will start by clearing aux and clearing variable 1. And at that point, we will have 0 and 0. And variable 2 still has number 3. Then it says, while variable 2 is different to 0, increase aux and decrease variable 2. So this means it will increase aux because variable 2 is different to 0. Then we will increase aux to 1 and decrease variable 2 to 2. And that's it. Then we evaluate again. Does variable 2 is different to 0? Yes. Okay, then increase aux and decrease variable 2. And again, last loop, we will check again if variable 2 is different to 0. Yes. And then we will increase aux to 3 and decrease variable 2. And this time, if we check if variable 2 is different to 0, no, then we finish the while loop. Then we start the next loop that says while auxiliary variable is different to 0, which is different to 0, then we increase variable 1, and variable 1 goes from 0 to 1, and then we increase variable 2, which goes also from 0 to 1, and then decrease aux. And to decrease aux is 2. And we check on aux is different to 0, then we loop again, and then we increase variable 1, increase variable 2, and decrease aux. Still aux is different to 0, so we go again, we increase variable 1, increase variable 2, and then decrease aux. Because aux now is equal to 0, then we finish. And then we finish with the same value that we want to copy from variable 2 to variable 1, 3, and 3. And that's it. So it might be a complicated way just to copy the value of some variable to the other. You know, here in this subject, we like to complicate things even for a simple sum for adding up. For addition, we saw the complicated way of adding. So now we are studying the complicated way of assigning a variable value to another variable. But this will pay, and this pays because whenever we do this, then we are guaranteeing that everything that we do is based on these variables, on these initial instructions. So it looks like the initial functions, you remember, 0, projection, successor. It's kind of that way of reasoning. And now we will match both of them. We will try to do the following. Imagine if we can implement the initial functions, and if we can implement the different mechanisms of combination, composition, and primitive recursion, and we can implement minimalization, then you know what this means. If we are able to implement those functional mechanisms with these functions, then it means these 3 functions will be the most powerful functions we need, and then we need no more. That's what we are doing. So you see why this is important. Okay, so let's start. We will start by defining the function 0. And the function 0 is handled by clear. So we just need to do some clear. And clear who? So we will now do some standards. So our standards will be that the input will be always given by x1, x2, xm, and the output will be given as z or z's, z1, z2, c2, c3, etc., up to zn. So this is to give or to map a function that goes from m tuple to the n tuples. So you thought you would get rid of these k, m, and n. Well, no, we still are using them. That's why at some point I asked you to pay special attention on these values. And at that point, for example, Dima complied that, well, why do we have to do some positional reasoning on the tuples? Well, now this is why it has some logic in it. So in order to see more why input and output have or are working within input X and output Z, then let's consider the successor function. I cannot. The successor function is handled by first copying the input number to the output number. That's it. The input is given by X, and the output will be stored in Z. And what we have to do now is just to increase Z. And that's it. You see, it works, right? So this, if you consider this successor function that has some X and it will yield something like a Z, you can regard it something like this. But this is abusing notation, so I will erase it so that I don't get blamed afterwards for misusing mathematical notation, which I think sometimes I do, but well, don't tell anyone. Okay, so finally, the projection function that we have defined previously, well, it's pretty easy, because what we want is just to return as the first element the J, how to say, X, the jth element. Yes, so we have the element number J, which is this one, and then we just return it as the first element. It's just a copy, and that's it. So you can see that projection can be defined very easily in terms of this basic programming language, or Barebones programming language. So that's it. So far, we have been able to implement our initial functions in this basic programming language. Okay, now we have to show that we are able to implement all the mechanisms for creating the partial functions. So we will consider two partial functions, one going from K and going to M, and we will consider a different function which goes from a K tuple to a N tuple. Remember that whenever we use this, these are tuples, you know this already. And then if we want to compute F cross G, then the only thing we need to do is to execute the first program, and then execute the second program, and then store its results. We move them, move the results to the latter part. So let me see if there is an example here. Remember that this, when we are using this operator, it means that the output is concatenated. So the output of F will go first. So the first M elements are the output of G, and then I will use a different color. And then the elements of, oh my God, of G are given here. And this is just by position, and these are N elements. Yes, remember that this operator that is composition, yes, composition, it will give you the results of G move to this part, and the results of F move to this part. So you can imagine, or you can think of a program that is called G. And this program then, after it's executed, will move all of its outputs. For example, let's say that G has N outputs, and you have to shift them by M positions, meaning that the output that remember that we are obtaining all outputs as Z. Yes, then the Z1 must be moved to the M plus 1 position. Why m? Because we need to make space for the result of f. So we shift, when we first execute G, the result of G will be given as Z1, Z2, Z3, etc., up to Zn, right? So we have n values for the output of G. So we will take, you can see, imagine that this is here, 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 so we need to shift them. In order to shift them, we just add m numbers to them so that they are moved. So that's why this output, which was Z1, now will be moved by m positions to the right so that it gets here. So this will be position Z m plus 1, Z m plus 2, Z m plus 3, etc., until reaching m plus n. And then we have free these positions. We have this position free, and then we can use them. So let me just write this. We have to move one by one. Z2 is moved to Zm plus 2, and finally m plus n until we reach n. So by this fragment of the program, what we are doing is moving the outputs of this to the right. It's that simple, no more. And when we have moved them, then we are able to execute f. And then when we execute f, then automatically we will have these values filled. Z1, let me put with red, just to keep with the colors. So we will have Z1, Z2, until Zm. And this is the output of f, while the blue one will be the output of G. And just by using this program, then we are calculating f cross G. Yes, because remember, cross is just putting the result of one function after the other one. If you remember, you can say, for example, the what we can say, 0, and then we combine it by the projection of the second element of the 3 tuple, which is 5, 8, 3. So when we combine this, we will have 0, 8. So the first one, the first part will be 0, and the second part will be 8. When we compute this, we only move it to the right, we shift it by one position, and then we calculate this 0. Yes? This should be understood like 100%, because if not, it will get a little bit more complicated afterwards. But we are just moving them. And then we calculate G. Then we move the results to the right. And then we leave this space free so that we can calculate F. And at the end, we have a single vector with the first part being the result of F and the second part being the result of G. And that's it, because this is what this mechanism does. No more, it's no more complication with this. Okay, so now let's see the second mechanism, which is composition. So let me change here. So we will have two functions just to review composition, which is G is composed by F, and it consists of an L tuple and a G, which takes this L tuple as input and gives an M tuple as output. And therefore, G composed by F will go from a K tuple to an M tuple. Yes, so we have seen this already, and this is because we are taking as input this K, and then we will take it as an M. Okay, so in order to do this, then we first calculate F. So to calculate F, we will have a program that is F. And then the outputs of F will become the inputs of G. In order to do so, if we have, in this case, L outputs of F, then we have to move to the input number 1 the output number 1. So this is, not to confuse you, this is the output of F will become the input of G. So we must do this for all the outputs of F, which are exactly L. Why do we have L outputs of F? Well, because we know it's an L tuple. And why we know it's compatible with G? Because G has the same L tuple as input. Therefore, we will copy L times, or we will copy for the L outputs, we'll move to the input. And then we just execute G. And G will take the input of F, and it will output, it will yield the, just to put it here, it will give you Z1, Z2, until Zm as answer. And that's it. So you see the composition mechanism can be very easily implemented by using the functions we already know. That's it. Now the third mechanism we saw is recursive, primitive recursion. So we will see it now. So far, how are we going? Fine? Or so-so? Okay, thanks. Okay, so remember that recursive primitive recursion had a template that was very fixed. So we have the basic case being this, and then the following cases being calculated based on the previous case, like this. So we have three functions. We have h of x, which is a tuple. In this case, it will be a k tuple, a y, and we will invoke again this f with the previous value of y. This we have already seen this, so now we will let me write the size of the tuples. We have here that there is a function called g, which takes as input a k tuple and returns an m tuple, while in turn h will take as input a k plus m plus 1 tuple and return an m tuple. And finally, f, we will take a k plus 1 tuple and return an m tuple. So first of all of them return the same m tuple. And this k plus 1, remember that this plus 1 is because we have k elements here. So k elements, k tuple, and this will be plus 1. The same here, we have k elements because this x is a k tuple, and then it will take plus 1 element. And because this has no plus 1, so G only takes a k tuple as input. You can see it here. And the result for all of them is m, m, m. For h, we have k plus 1 plus m, because f will return an m. So if you want to draw it here, we have here, this is k, this is plus 1, and this is plus m, because f will have as output m elements. So h will take as input k plus 1 plus m, k plus y plus m plus 1. And this y is the number 1. So as I told you before, maybe it's easier for you to remember, but it's a bit weird, but it's easier for you to remember if we have k plus 1 plus m, just to keep the order in it. Okay, now that we have this, then we will implement primitive recursion by using our basic programming language. So first of all, we calculate G. Why? Because it's the basic case, the lower, the bottom case. And then we will use some auxiliary variable where we will temporarily store x k plus 1. So before I tell you, I want you to tell me who is k plus 1 here. who is k plus 1? Remember, this will be the first k elements, x1, x2, x3, and then when it finishes after xk, we have or maybe I can write here with a different color. You can see this as an input tuple, x1, x2, x3, xk, and then you will have xk plus 1. So these first ones map to k, and this one maps to, in this case, 0, yes, Oscar, but in general, it will map to y, right? So whenever we say here xk plus 1, we are talking about y. Why don't I say y? Why do I say xk plus 1 instead of saying y? Well, because remember that we are using our variables are only on the domain of, not the domain of, the name of our variables are only x for input variables and z or z for output variables. That's it. That's why we don't use y. Of course, we could use y, but this positional system allows us to know that within this tuple, because we are seeing this just a very, very large tuple, this is also a very, very large tuple, we are just accessing them by positional value. Okay, so this is y. Okay, so then we will erase y. We say clear xk plus 1. If you want, we can put it this like this in green so that you remember that this is y. And then our while auxiliary value, which was y, is different to 0, we will do the following. We will put as input as xk plus 2 the output of g, and then we will copy all these values until we reach k plus m plus 1, and I would say again k plus 1 plus m, it's easier to understand, and zm. So maybe at this point you say, why the hell is teacher doing this? Well, because this is the last class and this is the last time I can make you suffer, so that's why. Okay, so this is z1. This is the output of the previously calculated g. We have not overwritten it. So this is the previous output of g. And this is the second previous output of g. And this is the mth previous output of g. Remember that g has exactly m outputs, and no more, no less, because it's the definition of g. Yes, m can be 1, m can be 2, and can be any number, but in general terms, we have m outputs. So we are copying them into xk plus 2. Why plus 2? Well, because we have not seen yet, but what we want to do is to invoke h, the function h. And the function h will take as input first k elements, which is x1, and let me use different color, which is x1, x2, xk, and this will correspond to x. Then in green, because we said that y would be green, then we have x, really green. Then we have x to green, xk plus 1. This is this y, yes? And then finally, we will have m elements, xk plus 2, xk plus 3, until reaching xk plus 1 plus m. Why? Because f has m elements. Yes. So when we copy z1, z1, z2, zm into these ones, because we are preparing the input of h. The input of h will consist of k elements, then the number of y, and then all of this. And how do why I know I'm feeding the correct y here? Because at every point we are using this is y, and we have never, well, we have destroyed it, sorry, we have destroyed with 0. So the first time I'm feeding this value of y with 0. So I'm saying I'm trying to calculate after the basic case, I am feeding this value. And then I will increase, for calculating the next value, I will do increment x k plus 1 and put it in green so that you remember this is y. And then we will decrease aux. Why do I decrease aux? Because this is my counter. So that if I want to calculate for 3, then I will go back to the basic case 0 and calculate g, and then I will calculate for the remaining cases. In this case, for the basic case, I will return for y equals 0. Yes, in order to calculate for y equal 1. And then I increase y so that next time I will calculate for 1 based on 0, calculate for 2 based on 1, for 3 based on 1, etc. So maybe you want to do an example of this, or no, I think you don't want to make an example of this, but we have time, so we will do it. And let's see. Imagine, let's do something simple. Let's do an addition. So you remember, I will compress this. So this is a good algorithm of compression for reusing whiteboard space. So addition was given in terms of H, and you see also why it was important to use this template of F, H, and G, because this way we are able to translate it into this language, for example. So let's see. Addition, as we saw it, was given by, I'm looking for the original definition, here it is. It says plus x comma 0. So the g is given by the projection of the first number of the k tuple. In this case, our k tuple, the value of k is 1. And then we calculate the following value, which would be for y plus 1 equals to the successor of the projection of the third element of the 3 tuple from x, y, and plus x comma y. That's it. So now let's define each of them in our basic language, which is G. And G is defined as, let's use some colors. So this is G. So G will be defined as the first element of the one tuple. So this will be Z1. Yes. And that's it. Then if we define F, no, then we define H, and H will be the successor of the third element of the 3 tuple of the previous element. So in this case, this number will be F, and it will be defined in terms of the previous one. Let me think a little bit on this. Okay, so this is I'm not sure if we need to execute F here. I think it shouldn't be necessary. Because we don't need stacking. So let me just think a little bit on it. Yes, so we will have first the projection of this element. Remember that we have here, this will be the first k element, so this will be x1 and k equals 1. So that's it. So we will have here x2, which is xk plus 1, and then we will have this as x3, and this will be xk plus 1 plus m. And in this case, m equals 1. So we will return the third element, which in this case is z, which is x3. And then we need to do the successor. So remember that for this, we did increase z1. And that's it. So I wonder if this will work. Let's try it. I think something's missing, but let's try it. It looks so simple, but maybe it will work. So let's try to add up 5 and 3 as before. Let's say we want to calculate the addition plus of 5 and 3. So in this case, we will have our x1, x2, and z1. x1 is 5, x2 is 3, and we will use also an auxiliary variable. Our primitive recursion says we will execute here, and we execute g. And g says copy x1 to c1. So we copy x1 to c1. C now has a value of 5. And then our algorithm says the value of x k plus 1, which in this case is x2, which in this case is 3, store it into aux. So aux will have the value of 3. Okay, the next one says clear xk plus 1, which in this case is x2. So following the colors, it should be this one. And then it says clear this one. Okay, 0. Then while auxiliary is different to 0, then copy for each one of the m elements, which in this case, m is equal to 1. M equals 1. So we will do it just once here. Sorry, we'll just once. So we will copy the output of z1, which is 5. We will copy to xk plus 2. K is 1, so we will copy this to x3. Yes, so I need to consider x3. Let me move this. Okay, so we have x3. So far we haven't used x3, so we will move the value of x1 to x3. So now x3 is the same value of x1. And because m is just one element, then we don't need to do all of them. Now we will execute h. H says, copy the value of x3 to z1. Okay, it was already there, but then let's recopy it. And then increase z1. So now z1 will be 6. And that's it. Finish h and then increase y. Our y now is 0. Remember that xk plus 1 is this one. So now we increase this and its value is 1. And decrement aux, the auxiliary variable is 2. Okay, so sorry, I need to compress even more. the whiteboard because we are running out of space. Okay, that's extreme compression. And I will shift this upwards. I insist, this is very nice. I don't know how will I do it when I don't have this sort of magic. Okay, so we have decremented aux. Then we evaluate. Aux is different to 0? No, then we still execute. And then we have Z1, which is 6, and then we move to xk plus 2. Xk plus 2, remember that k is 1, so xk plus 2 is 3. If you need some colors to remember, then let's say xk plus 2, in this case, is x3. Okay, so we have numbers to remember, colors to remember. So we move this value of Z1, which is now 6, we move to xk plus 2. And that's it. Then we execute H. H says, copy, oh. Let me project again. I don't know what happened. Sorry for that. Oh, so sad, I cannot. Don't say it, restart your device, it says. Last try. Wow, it recovered. Thank you for your good vibrations. Okay, so we have so far, now we restarted, we copied to this and we were executing H. In order to execute H, then we have X3 move to copy to Z1. X3 copy to C1 and then increase Z1, which now is 7. And then we leave H and then we increase xk plus 1, which is Y. So this will be 2. And decrement aux. Aux now will be 1. And then we ask, is aux different to 0? No. Then we loop again. And then we copy Z1 into X3. So we copy Z1 into X3. Now it's 7. This is very old. Now it is 7. And only for M elements, M, remember, is equal to 1. So now execute H. H says copy X3 to Z1. Copy X3 to C1. And then increase Z1. That's it. Then we come back from H and then we increase Y. We increase Y to 3 and then decrement aux. Aux now is equal to 0. And because it's equal to 0, we have finished. So our result is given, not yet. I think I missed something. Give me a second. We are almost reaching. No, it's okay. And then we have our result. Yes, thank you. Our result is Z1, 8. So we have properly calculated plus of 5,3 equals 8. You see? So, well, if you thought that that recursive functions were very difficult or were a complicated way, then try to calculate them by using non-recursion. So you see, it's a bit crazy, but what we are trying to point is that we are able to calculate the primitive recursion by using the same elements we have using for our very simple programming language. Can you hear me properly? Because I see you moving slowly. Okay, thank you. Well, now you may say, how come this is cheating? Because you are using the stack for calling subprograms here, subroutines. And no, I can tell you, no, I'm not cheating, because you can copy this, you can copy it here, and you can copy the program for H, you can just copy it here. You don't need stacks to calculate recursion. You see, that's why primitive recursion is different from general recursion, because as you can see here, you don't need stacks to calculate primitive recursion. You see, it's a bit strange, right? Because we are taught always that for calculating recursive functions, we need a stack forcefully. And then we see here, no, there's no stack. Just calculate the basic or the base, the bottom case, and then from there build up. No need for a stack. So that's a bit surprising, but it works. I just did an example here, which if we try to do a different example, then you will see it gets more complicated, but I just want you to grasp the general idea, okay? Well, sorry for complicating your life again, but there is just one last mechanism that is missing for being written in this simple language. And that's primitive, no, that's minimalization. Okay, so let's change page. Minimalization can be calculated in a very simple way. We can do clear x k plus 1. And just to remember who is k plus 1, y, the same as before. Then we will execute some g, and then we will do while z1, this is the output of g, is different from 0, do increase g, and then execute again g. And that's it. If you find the 0, then just return x k plus 1. So this is g and this is g. And if not, then you will loop endlessly here, meaning that it's undefined. So very similar to Turing machines, in this case, undefined means that you never return a value. So remember, we have as minimalization, we have the minimum g for which certain function called g equals 0. So again, as before, if you regard this x, this is expanded to x1, x2, until xk. And of course, this y will be xk plus 1. So now you are very used to this, so no problem for this. Then what you do again is clear y. So we start looking from y equals 0. Then we execute the function g, which is defined somewhere as we want. And then we try, if the output of this g, remember that the outputs are giving us z's. So if the output is different from 0, because we are looking for 0, then we increase the value of g. Then try for 0, for 1, for 2, for 3, and execute g again. If we find the output equals 0, then return the minimum y for this value. So if we examine for the division, for example, which is the only function we have seen so far, there are many more, but we only saw division here. Let's try to do the exercise. We have division defined as the minimum t for which x plus 1 minus mult. We have seen this already, so this is just to practice here. So maybe I won't try to define g in terms of this. You can, as the book says, the exercise is left to the reader. So this is very convenient way to say we will not cover it here, but you can do it really. So this will be G.
Sorry
And
to interrupt you, doctor, but your screen is not updating.
My screen is mean. Okay, sorry. So this is division, and this will be G. Thank you for telling me. And then in this case, T will be a third variable. So this is why it is important to count how many. This will be x1, this will be x2, and this will be x3. So this is xk plus 1. So in this case, we have this as our green friend. This is here, it's not called y, you see. Then we start calculating this. We say, okay, clear t. So by saying we have x1, x2, x3, and we have, of course, the output. So at the beginning, we are trying, if we want to do this exercise with divide 5 by 2, as we did before, then the value of x1 is 5, the value of x2 is 2, and the value of x3 is we don't know, and we don't care now, and the output is not, it can be defined, but we don't care. So we start with clear x plus 1. And remember that our x plus 1 now is x3. So clear this, and now it has the value of 0. Then we execute G, and G says x plus 1, x, in this case, our x will be x1, and y, this is x3, and y is x2 and x2. So x1 is 5, 5 plus 1, 6 for our example. So now we have 6 minus, and we have this is x3 is 0 multiplied by 2, well, it's 0 plus 2 is only 2. 6 minus 2 is equal 4. So G, after executing G, Z1 is 4. And then it asks, is it different to 0? Yes. Then increase xk plus 1. So we will increase, we will increase this one. And then we execute again. We will have x1 equals 5. So again, we have 6 here, and minus x3 is equal 1. Here equal 1 multiplied by y is 2. So it's 2 plus x2 is 2. So we have 2 plus 2. We have 4. 6 minus 4 equals 2. So now we have all our results here. So Z1 is 2. And we are executing this one. Is Z1 equal 0? No. Then increase xk plus 1, which in case is x3. So this is 2. And execute G. Execute G. We have not defined G in very detailed way, but we are executing it here. So now we have 6 minus, and we have x3. Now the value of x3 is 2. 2 times x2 is 2 times 2 is 4 plus x2. So this is 6. 6 minus 6. So this is equal 0. So now after finishing execution of G, Z1 equals 0. Then we comply with this condition because Z1 equals 0. Then we stop, and then finally we return this x plus 1, which is this one. We copy it into the output. So the output of this is 2, meaning that the answer of the division is 2, which is correct, as you remember. Okay, so far we have shown that we are able to implement in our very, very basic or simple language, we are able to implement all the mechanisms here, shown here. So we have started by defining the initial functions. We have defined these mechanisms and including, where is it, minimalization here. We have defined 1, 2, 3, and 4 mechanisms. So now we can say we can reach all computable functions by using our simple, very simple programming language. And remember that our programming language started just by these 3 simple instructions. So next time you walk into a bar, you can talk with a pretty lady or pretty boy next to you and tell him, do you know how many instructions the very simplest programming language has? And he will say, no clue, or she would say, no clue. You can say 3. And then you can start talking about this. Maybe we should put this into YouTube so that you can show the video, or you can do your own video. And you will say you will have success in that pickup line. Okay, well, jokes aside, you can see this is very important because we are used to think that the more instructions a language has, the more powerful it is, right? But talking about computing power or the power of computing results that we need only 3 instructions. And I think that's surprising. Well, the first time I saw this, I was shocked, like the meme that says like exploding head, because it's too simple. How come all the power of computing power in the universe is started just by these 3 instructions? And of course, it has also a lot of implications. There are variants. These are not the only basic building blocks. Sometimes instead of having a while, you can have a for, or different things. If you want to explore this, you can do exercise. This is not homework, but if you are interested in this, you can do exercise number. There is an exercise here. Give me a second. Exercise number 1 on page 233. Exercise number 1, page 233, of course, of the English version. And it has a loop instruction. It has clear, increase, and loop. And from there, you can build again all the other things. So it has not increase, decrease, and while. So it says clear, increase, and loop. Loop the variable, and you say how many times. You see, it's really different, but it's also interesting that with this, you can create all the power again, but with different ways of constructing it. So it would be interesting, well, of course, if you are interested, but that you try to build all the initial functions, all the primitive recursive functions, and also the partial recursive functions by using these 3 instructions. So, well, that's it. So tell me, what do you think? So this is the content of thoughts. After...
We are speechless.
Okay, well,
mind-blowing.
Well, I hope you enjoyed this. This last part, well, I enjoy, of course, all the course. I hope you enjoyed it as well. But this last part, I think, is very interesting because it has a lot of implications, because I think all of us are programmers and we are using lots of programming languages, even Java. But and it results, all of them have the greatest power for programming. Well, of course, if we talk about expressiveness, Maybe you need object-oriented programming, maybe you need functional programming, maybe you will need other things, right? I'm not saying that all those beautiful and nice things are not needed. However, you can always go back to very simple instructions. And also there is a part that I'm not covering in this course that of course can be helpful to you, and is the fact that you can do the same as we did with our simple programming language with Turing machines. And then you demonstrate that the initial functions, the primitive recursive functions, and the partial recursive functions can be implemented in a Turing machine, and vice versa, that you can implement a Turing machine by using primitive functions. This is interesting because if you show in one way and then you show into the other way, then you are demonstrating that both theories are equivalent. And this is done, also in Berkshire. If you are interested, you can see also the last part of the chapter. So we don't see it here because of time restrictions. You can see we are finishing on the edge of the time. So we have to finish this course. However, I think all those things are interesting. And well, just to finish, may I invite you to the next course we will be giving. The next, well, of course, it's not so technical or so theoretical maybe, but if you enjoyed the talk about the Goru machine and things like that, like make you think in some sort of philosophical ways, I will be lecturing artificial intelligence and society. Probably it will be in Spanish only. I don't know yet, but well, but anyway, I want to invite you. Well, so I couldn't avoid the commercial at the last part. So as always, well, I always thank you for your attention at the end of each class. But well, this is the final thanks. And also thank you for being such a nice group. Thank you for participating, for submitting your homeworks, for giving